All right, friends, I believe we are live on YouTube. I am going to go ahead and start the webinar so that way attendees can join us. And you let me know when you want to kick it off, but I can let you know how many attendees we have right at the 1 o'clock mark. But I am turning it over to you and I am going to start this webinar.
Welcome, everyone. I'm excited. We see lots of people coming. We'll get started shortly. All right, we're waiting for a few more people, and we'll get started. Well, welcome everyone to the 34th Annual Chemistry Day, co-sponsored by the Kalamazoo Valley Museum and the local Kalamazoo section of the American Chemical Society. And I'm excited to host this today. My name's Annette, and I'm the program coordinator here at the Kalamazoo Valley Museum. And I have our couple co-hosts here. I have Amy, who is the corporate trainer at the Groves for Kalamazoo Valley Community College. And I have Paige and John. Paige is in the provost and vice president of instruction and student services for Kalamazoo Valley Museum. And her husband, John, have both been chemists in the past for our hands-on programs with Chemistry Day. So we are excited to have you here as well. We do have two interpreters today. So we have Audrey and Justine, who will be interpreting, and all of our videos are also closed captioned. So we are excited for everyone to be able to participate and have fun. So we're going to start out throughout today. We'll have several videos and a chance to introduce them and talk about them afterwards. But we're going to start out with a welcome message from Dr. Washington, president of Kalamazoo Valley Community College, followed by a short history of the Kalamazoo Museum Chemistry Day and National Chemistry Week by Lydia Hines, the founder. So we'll get started now.
Greetings. I'm Marshall Washington, president at Kalamazoo Valley Community College and our Kalamazoo Valley Museum. I'm delighted to welcome you to this national celebration of the Chemistry Week and this, our virtual Chemistry Day event. Many volunteers work behind the scenes to make this event a reality, and I thank them for their efforts. Today, professional chemists will lead virtual hands-on experiments you can do at home to solve a family-friendly mystery. While we would have preferred to meet with you face-to-face, we are hopeful that you will find these activities engaging, educational, and fun. Together with the local chapter of the American Chemical Society and other collaborators, we encourage you to expand your understanding about the role that chemistry plays in our daily lives. The college offers a number of chemistry courses for students of all ages, and perhaps you too could participate as a chemist in future Chemistry Day programs. We have expanded our science offerings to include courses in the health and medical field, culinary arts, and wind science, to name a few. If this program whets your appetite for science exploration, visit the college website for a list of course offerings. Enjoy the day, and thank you for joining us.
Here's a story that got its start in the last century, and it's still going on. I had been actively doing chemistry and demonstrations and talking about science careers in elementary and middle school classrooms in Kalamazoo and Portage for a few years. And then one day in late 1986, a long time ago, as I was looking at the brochure for the activities at the Kalamazoo Valley Museum, I noticed that the physics department at Western was doing a hands-on program there. That piqued my interest, and I became a copycat. That was approximately 35 years ago now. The museum was still at the second floor of where the Kalamazoo Public Library is today. Well, anyway, so I asked the then program coordinator at the museum, Cheryl Lyon, if chemists could set up a similar program. And she said, sure. And that was when we got started. I asked chemist members of the Kalamazoo section of the American Chemical Society to give up their time on a Saturday afternoon to present an activity which they thought children would enjoy doing and the public at large would enjoy appreciating the positive aspects of chemistry. And that's when the start of our Chemistry Day began. 2 years after the start, Annette Hoppenworth joined the Kalamazoo Valley Museum staff, first as a helper with the chemistry program, and then, after Cheryl's departure, she became an invaluable champion of our annual hands-on program, even as they expanded to their beautiful new and larger facility. As an outreach event on a national scale, it was formally started as National Chemistry Day in the fall of 1987 by that year's American Chemical Society president, who was a faculty member at the University of California in Berkeley. That was the fall of the year that we had started ours. So we had a second activity that year. And we have been doing this in-person program every year since then, until this year, of course, when we have to do it virtually, and you will be doing these experiments at home, following some. Mrs. Hoppenworth has an activity plan for you, and everything will be a lot of fun doing these things at home with your family. After about 4 years of National Chemistry Day, the American Chemical Society expanded the program, so it gave opportunity to do activities for a whole week, and its name changed to National Chemistry Week. And in the last 10 years, National Chemistry Week has been celebrated in October, and it often includes Mold Day. National Chemistry Week is a community-based program of the American Chemical Society that unites all stakeholders in the society, local sections like Kalamazoo, international chapters, student groups, technical divisions, businesses, schools, individual members. in an annual celebration of the importance of chemistry to each of us individually and all of us collectively. Since 1987, the American Chemical Society has dedicated an office whose staff develops written materials and other helpful educational resources vetted very, very rigorously for safety before they are published for various age groups. And you may access those materials. Many of them are free to you at www.acs.org/education. I repeat that, www.acs.org/education. It's always a delight to see the enthusiasm, curiosity, and anticipation of the youngsters as they come with their families or with other groups, ready to learn new concepts and to do experiments. They love to do experiments. I always say children are the best scientists until we start tampering with their curiosity. Anyway, I've been doing this long enough that occasionally I see parents, and yes, even grandparents, who introduce us to their young children, young friends whom they bring to the event with the hope that they will enjoy it and learn as much as they did when they were children. Well, anyway, that's what we want to continue to leave as a legacy in Kalamazoo. So have a fun time this National Chemistry Week doing the activities that Mrs. Hoppenworth has arranged for you and watching online the demonstrations that I've presented for you. Thank you.
Welcome back. We have set today's Chemistry Day program up as a mystery. So it's giving us a chance to get to know you and for you to get to know us on our Kalamazoo Valley Museum website, which is www.kalamazoomuseum.org. At the very bottom of the page, you will find a link to the Chemistry Day page, which will have the PDFs for images of all of our staff and their story, which you're going to hear later, pictures of all of the exhibits that are involved, and all of our chemists and their experiments. You're going to see all of these as we do our program today, but to refer back, we are going to ask you to help solve this mystery. So we need you to follow through and see if you can figure out what happened today. And you'll be able to use the experiments to do that. But first, we're going to recruit you. You guys are now all gumshoes. And a gumshoe is a term that was first developed in 1913 to describe someone who's very good at being quiet. And it refers to tennis shoes before they were made. They were called gum. Thank you. We've got our two gumshoes there and a third here. So they were originally thieves who could be quiet and quickly became the detectives who were actually able to sneak up on the thieves because of their quiet shoes and catch them. So we're going to give you an opportunity in your packets. We've got some photographs of different historic gumshoes. Probably the first one that Paige and John and I are all pretending to be is Dick Tracy, an early detective and also a cartoon. There you go. So you can color that. Another one is Sherlock Holmes. And I know most of us know who Sherlock Holmes is. We have Agent A from the Men in Black, who is also pretending to be a gumshoe. So I want you to work with your family or your friends as a team, and you are going to become your own detective agency, and you're going to help us solve this mystery today. But the reason why we want to include you is because this museum belongs to you. And we have a message next from the director of the museum, Bill McElhone, who's going to explain why this museum is all yours. All right, we had a little technical difficulty there. I hope you were.
Donations from as small as $10 to larger donations in the multi-millions. Because of that wall, this is truly, and all the donors on that wall, this is truly your community museum. So you can take ownership in it, and we're going to rely on these owners to help solve today's mystery. As we go through today's program, I do want to thank the many scientists and volunteers in coordinating this event, certainly the local chapter of the American Chemical Society and other scientists who are participating, and all of you who are participating with us. And we hope that we'll solve this mystery, hope that you had fun, and we do look forward to having you back here at the museum very soon. Thank you.
Welcome back. So for today's mystery, we are following the story of the Sticky Bandit, a thief who likes to break into museums, but instead of stealing things, he rearranges the artifacts and the exhibits, and he leaves behind gooey substances and frames one of the staff. This year's National Chemistry Week theme is Sticking with Chemistry, and it talks all about adhesives. So before we get to the exhibits, I want to give an opportunity for you to meet some of the museum staff here. We're going to start with a couple videos from Brittany, our collections registrar, and she's going to update you on some of the things that we're doing to our exhibits to prepare for reopening and for your return. She's also going to share just a short glimpse of our fourth floor collections, something that is not open to the museum staff or visitors most of the time. So we're going to start with that, and then we're going to go to our newscast live from the museum, where newscaster Sara Slippery is going to introduce you to the exhibits and collection staff. All right, pay attention because you're going to want to know who these folks are. Enjoy.
Hi, my name is Brittany. I'm the collections registrar here at the Kalamazoo Valley Museum. I work with our collections and exhibits team to make sure all of our artifacts are safely displayed for all of you to see. I'm here in our second floor history gallery to show you some of the cool new technologies we've been working on while we've been closed. Behind me is our switchboard exhibit. Normally you'd come up, pick up a telephone, and listen to a story. What you're going to be doing when you come in to see us next time, you'll be able to use your smartphone to scan a QR code, which will bring you fun and interactive activities right to your phone. Some of the other things we've been doing here in the History Gallery are working with our instruments, which normally you can come up and play. But what we'll be doing now is installing a smart projector that will actually allow you to interact with musical themes without having to touch anything at all. The other thing we've been working on here in the History Gallery are our touch kiosks. Instead of touching, you'll actually be able to come up to the kiosk and watch a video on a loop that will explain some of the history and other fun things here in the gallery. In areas like our general store and our diner, we have gone ahead and removed some of those touch and hands-on objects, and we're going to be installing historical imagery instead. The exhibits team has been exploring infrared technology. You'll be able to walk up to some of our exhibits and just with a wave of your hand or a tap of your foot, interact with that exhibit to see additional text, video, and images. What's great about this new technology and bringing things to you digitally is we're able to go ahead and capture different parts of history that aren't on our labels currently. We're also able to bring you additional information in other languages. Our exhibits and collections team can't wait to see you back here in the museum soon. And when we do, we'll all be safe. Welcome to our collection storage area. Here in this secure space, we store over 50,000 artifacts when they're not on display in the museum. The noise you're hearing behind me is from separate air handlers and HVAC units that are specific to this space in order to keep the temperature and humidity just right for the artifacts. This space is not only used for storage, but it's a workspace for our collections team as well. Here, we can scan documents and photos to add them to our online collections database, which you can access from home through our website. On the database, there's over 26,000 items for you to explore, from three-dimensional objects to textiles, photos, documents, and more. We also prepare artifacts and textiles for displays and exhibits. Here, we sometimes dress mannequins or prepare condition reports for objects that will go on display before they're seen by you in our exhibit spaces. The shelving that you see behind me stores thousands of artifacts, everything from objects to textiles, photographs, and documents. Our textile collection is displayed on hanging racks with padded hangers to make sure the fabric is kept safe and secure for future generations to enjoy. Different artifacts have different means of storage. Some are kept in acid-free boxes, others in acid-free sleeves, or on open shelving. Each object has a specific location here in storage, so our collection staff can easily access any of our 50,000 items at any time. While we've been away from the museum this summer, the collections team has still been actively working with researchers and donors. Donors who have objects that they might like to see here at the museum reach out to the collections team, where we discuss with them the history and provenance of the items that they have and how they fit with Kalamazoo history or the history of the Southwest Michigan region. Usually the collections team receives approximately 150 donation offers every year. Of those offers, only between 30 and 50 collections are actually accepted into the permanent collection. Each collection can range from one artifact to dozens in a single donation. When a donation comes into the museum, each artifact in that collection is reviewed for condition, studied, and researched for historical connections and interpretation here at the museum, and then given a permanent home and location here in collection storage. While the museum has been closed, our staff has been working hard bringing more objects to you at home. We've been adding more items to our online database, as well as utilizing artifacts that were meant to go on exhibit when we were closed to create online exhibits, such as the 40th anniversary of the Kalamazoo tornado exhibit. This exhibit features over a dozen artifacts, from newspapers to books to photos of that tragic event. We're working hard on collecting, preserving, and sharing the history of Kalamazoo with you, no matter where that might be. We hope to see you safely in person real soon.
This is Sara reporting to you live from the WKVM Newsroom. Notorious criminal the Sticky Bandit has chosen the Kalamazoo Valley Museum as his latest target. He is known for breaking into museums, rearranging the artifacts and exhibits, then framing one of the museum staff members for his mischief. The bandit is notorious for leaving behind a series of gooey clues, which can lead to or distract from the true evidence of the case. Local authorities have requested your help in solving this mystery. The WKVM news reporters have been interviewing museum staff to figure out which one has been framed for the crime. Let's introduce you to members of the collections and exhibit staff. Regina Collector holds the position of collections manager. Miss Collector has her sights fixed on the community, making sure the collections incorporate the diversity of all who live here. While adhering to strict guidelines and embracing national standards, she maintains a community-based collection that unites the story of both historic and current inhabitants of Southwest Michigan. Brittany Taylor is the collection's registrar. Bound to details, Brittany meticulously searches and documents the story behind the art, artifacts, and documents in the museum's collection. She cleaves to historical facts, unites images with recorded documentation, and fuses all the details together. Nothing slips by her eagle eye for detail. In the exhibit department, we next go to the design assistant, Alicia Font. Gripped with a need to see the big picture, she creates cohesive signage that bonds the eye-catching graphics with logistical details. Mrs. Font also searches for hands-on traveling exhibits to merge into the museum space for the enjoyment and exploration of all visitors. The two exhibit technicians work closely together. Tom Techno, a futuristic tech whiz, is constantly embracing new and updated technology to increase the accessibility and safety of museum exhibits for visitors. Mr. Techno's heart is linked to sustainability and protecting our natural resources. He grips the most difficult issues and finds a way to link museum resources with practical solutions. Watch out, Bob the Builder. Zach Wood has skills you've never seen. In his state-of-the-art workshop, he builds and repairs exhibits. He often incorporates improvements to the museum's traveling exhibits while installing them, fusing his fine craftsmanship into exhibits across the country. Who do you think the Sticky Bandit may have framed? This is Sara Slippery on the case, along with all of our viewing audience. Stay tuned as we meet the staff from the Education Department next time.
Welcome back. Next, we're going to hear from Lexie, our Program Education Department Vice Assistant Director. And she's going to tell you more about what we at the Education Department do in terms of supporting exhibits and reaching out and making connections with our community. After that, we will hear about and be introduced on our newscast of the education staff. Let's go hear from Lexie now.
Hi, I'm Lexie Schroeder Kobb. I am coming to you from Kalamazoo Valley Museum's third floor mummy exhibit. You'll be able to visit this exhibit next time you come into the museum. I'm the Assistant Director of Programs here at the museum. We explore many topics here, and the mummy exhibit is a great example of that. Here we explore subjects like history, culture, science, and technology. Much technology is used to explore and learn more about the mummy in this collection. Now today, our topic is chemistry, but we do all sorts of fun things here with programming and education at the museum. It might be artists and storytellers, it might be scientists and botanists, it could be any number of things. As long as we're having fun and exploring together here at Kalamazoo Valley Museum, we are meeting our mission.
This is Sara Slippery reporting to you live from the WKVM Newsroom. We have been investigating the criminal activity of the Sticky Bandit at the Kalamazoo Valley Museum. We continue our report today on the educational staff in hopes of figuring out who the bandit has chosen to frame. Local authorities are requesting your help in solving this mystery. Our investigative reporters have met with the educational staff and determined they are a unique group of individuals. It's up to you to decide if one of them may have been caught the attention of the Sticky Bandit. We caught up with Science and STEM Education Coordinator Kathy Botany in the museum courtyard measuring the sunflowers. Miss Botany, a previous teacher and Challenger Learning Center flight director, now produces science-based programs for the museum's Innovation Lab. She is affixed to hands-on learning, science exploration, and discovery. You can often find her fused to the rain garden exhibit outside, observing the native plants and recording their growth. Steve Galaxy, the theater and planetarium technologist, is often buried among stacks of computers, with his attention glued to the solar system. The museum's Digistar 6 planetarium system is an educational playground for technologist Steve Galaxy. Whether he is bound for the stars or affixed to his equipment, his computer savvy has been leading the way for virtual tours of the night sky and lively Zoom meetings. Planetarium and theater manager Mark Meteor not only orchestrates planetarium shows and schedules, but he is also a walking encyclopedia filled with amazing facts. While Mr. Meteor has his feet cemented to the ground, his mind clings to the stars. A lifelong teacher, he always has a great story to tell about his rock collection, his rocket models, and don't get him started on his fossilized dinosaur poop. He's always on the lookout for new planetarium shows that will attract visitors and leave an impression that sticks with them. Next, we had a chance to meet with the energetic Megan Reel, the museum interpretations manager. Miss Reel leads the frontline crew in meeting the needs of museum visitors. She is the glue that holds together the staff, schedules, front desk sales, interactions with visitors, and so much more. New ideas ooze from her continuously as she strives for staff excellence and the greatest of visitor engagement. After participating in a spontaneous game of hide and seek, we were able to speak to Anna Exploration, the museum's weekend and programming coordinator. Full of pluck and curiosity, Miss Anna's playful personality embraces the child in all of us. She leads the staff in examining the exhibits, creating dynamic demonstrations, and pushing the limits of play for visitors of all ages. She puts the fun in funtastic. Who do you think the Sticky Bandit may have framed? This is Sara Slippery on the case, along with all of our viewing audience. Stay tuned as we go inside the Kalamazoo Valley Museum, where local chemists were invited to tell us more about some of the gooey substances and clues left behind by the Sticky Bandit.
Welcome back. Before we get started on our experiments, we do need to talk about safety. Safety has always been an important part of Chemistry Day, and we've always had a chemist devoted just to checking out all of the experiments to make sure we are following safety guidelines very closely. You will notice if you purchased a resource bag that you have safety goggles that you can wear for your experiments. So we want to make sure you do that, but we also want you to know all of the other safety items that you need to be familiar with. So before we get started on our experiments, let's hear a little bit more about safety from Sean and Connie.
Okay, today we are talking about safety. Now, safety is very important in a lot of things. If you're working with chemicals, we have some specific things that need to be done. The biggest concern about safety with chemicals is splashing and things that might damage your skin if you get in contact with it. There are some others which we will cover in a little while. So, from head to toe, to get properly dressed for working with chemicals, you need safety glasses or safety goggles. Goggles are preferred. You should put on a lab coat. Not only will this give you an extra layer of protection, but it'll also help keep your clothes from getting damaged if you should accidentally spill some chemicals on you. You should have gloves on because certain chemicals can burn, even some common household chemicals. But when you're working with them as chemistry experiments, you need to have glasses, gloves, coat. You should also make sure that you have long pants, including socks, and shoes that cover your entire feet. No open-toed sandals or anything like that. Later on, as you go through the videos, you will see a video we did about Oobleck. And in that, you're going to see the importance of wearing this equipment. Now, the other things you have to be concerned about is heat, whether it's an open flame or a burner or something like that. So, if you are going to work with those things, you have to be aware not to get too close to them. Otherwise, you might get hurt. If you're a person who has long hair, you need to tie it back because your hair can burn very rapidly if you get it into a flame. If your religion requires you to wear a headscarf, you should make sure that that is tied back as well. We don't want to make so you can't follow your religion, but we do want you to be safe. And along that line, if you are in a religion where you have to wear a looser clothing, that's another reason for wearing a lab coat, is it will keep all of the loose fabric where it's supposed to be and not possibly getting ignited. So as you go through these videos, please follow the instructions on the safety that we've given you. It'll make your mom and dad feel a lot better if you are safe when you're doing these experiments.
All right, are you ready to get started? The meat of this program are the experiments. So we want to get right into that. We've got 10 different experiments we're sharing with you today. There are a whole variety of them in your resource bag. And as we touch on some of the experiments, if there are samples in your bag, we're going to share that with you as well in between and tell you all about them. So we're going to start, since this year's theme is sticking with chemistry. Let's start with Julie and how to make glue out of milk.
Hi, I'm Julie Bauer. I'm a local chemist here in Kalamazoo, and today we're going to make glue out of milk. So when you're getting ready to do this experiment at home, the first thing you have to pay attention to is safety. So you want to make sure you get a good pair of safety glasses on if you have them. You might want to wear an apron or an old shirt over your clothes to protect your clothes, or a lab coat if you have one. And the other safety issue that's real important is the heating of the milk. Don't heat the milk without a parent or guardian unless you have permission to do so. You can heat it in a microwave or in an oven, but be sure that you have a hot glove or a hot mitt so that when you touch that milk container, it won't burn your fingers. Okay, so let's make the glue. The first thing you do when you're baking a cake is you get all your parts together. Make sure that you have every ingredient that you need. So today, we're heating our milk here on this magnetic stirrer, and we have glasses to hold our milk product as we're making the glue. A fork for mixing, some measuring spoons, milk, vinegar, baking soda, water, and some paper towel to filter it. You can also use a coffee filter to filter it. So the first thing you do when you're making moo glue is you heat the milk. This is the type of heater we would use in a lab. It has a big heater underneath and a magnet. That magnet interacts with a magnet that we put into the milk that allows that milk to stir, and it heats it up as well. If you have a thermometer at home, you can test the temperature of your milk. If you don't, that's okay. Just make it warm to the touch. Once your milk is warm, you want to transfer that milk to a cup or a vessel of some sort that won't melt because of the warm milk. Just pour that right in there. Okay, and then the first thing we're going to do to that milk is we're going to add the vinegar. I put the vinegar into this little cup so that it would be easier to measure. 2 teaspoons of vinegar go into the milk, and we mix it. Now, I chose to use a fork instead of a spoon because when you use a fork, it's easier to mix and it breaks the chunks up. Can you see what's happening in here? That casein protein that's in milk is denaturing. It's becoming a big glob. The solid part is called curds. The liquid part is called whey. So we want to use this curds to make our milk. Now, when you do this at home, you might find that you have smaller pieces or chunkier pieces. It doesn't matter. It's just as long as you have those solids. I'm trying to get this off of here and it's not coming. There we go. So now we take the solids and the liquids and we filter them into another cup. When you filter them, you want to use a paper towel or coffee filter. You place the paper towel over your cup and put a little indent into the paper towel where the solids can form, like a little cup on top. And you want to be sure to hold on to that paper towel, because if you have a big chunk of curds and you put it on the paper towel and you're not holding it, the whole paper towel will go into the cup. So now let's filter our curds and whey. The liquid will go all the way through. And the solid stays on top. Now we want to take that solid and put it back into the empty cup. You just scoop it right up or scrape it off if you have to scrape it off. Now you have the solids and you're going to add baking soda to make your moo glue. We add 2 teaspoons of baking soda. 1 teaspoon, 2 teaspoons. And we get our trusty fork and we mix that in. You want to get this baking soda really mixed in with those curds. Now, a lot of the time, it's too dry at this point. So you want to add some milk, some water to the curds. Now, don't add too much water at once, because if you do, you won't be able to get that water out and your glue might be too thin. So just add a little bit of water. You can always add more water later. And we mix the curds in with the baking soda and the water, and we break it up as best we can. Now, while I'm breaking this up, let me tell you a little history about casein, the milk that we're making this glue out of, the protein from the milk that we're making this glue out of. Casein was used in ancient Egypt to build boats. It was used for that because it's very strong and is waterproof. So when it came along the time for World War II, they used it to waterproof airplanes, having learned from the Egyptians about the waterproofing capabilities of casein. So this protein from milk, casein, it makes your body strong and it waterproofs airplanes. Pretty cool stuff, huh? So now you can see that the glue or the baking soda and the casein are mixed in real well together, but it might need a little bit more water. So we add a little more water and we mix it some more. Now, as a scientist, which all of you can be, you want to play a little bit. You can ask yourself, what happens if I use milk that has fat in it, like whole milk? What happens if the milk isn't warm? What happens if it's too warm? What happens if I add more vinegar, more baking soda? How does it change my curds? How does it change my glue? Is my glue more consistent? Is my glue stronger? All those kinds of questions you can play and ask as a scientist. All right, we've got our moo glue here. And now you can use that to glue things together. Now I played with my moo glue a little bit after making it, and I took 2 pieces of wood and glued them together. This glue is so strong, I can't pull it apart. So go on, go play at your house and have some fun.
Welcome back. So in your resource bag, you are going to find several different types of adhesives. There's a bottle of glue and a glue stick and a pack of Post-it notes. And because there's so much related to glue and sticky chemistry. The resource bags also have the American Chemical Society magazine for this year, which you can also find on their website. And it lists all the different descriptions of glue and the different types of glue. And I'm wondering, what is your favorite type? So Amy and Paige and John, can you talk a little bit about what your favorite type of adhesive is?
Not really sure. I'm thinking about it. I like to make lots of notes. So probably I'm a big fan of Post-it notes.
Oh, me too. What about you, Amy?
Post-it notes are cool. They're really, really useful, but I gotta say, I'm a fan of tape. Duct tape, the crafts you can make with duct tape. Oh my gosh, they're so fun. We've made hats, we've made ties, we've made like theater props. They have so much duct tape and it is so sticky. Wow. Although I gotta say, I don't like tape when my mom wraps presents. She uses so much tape on her presents. It's so hard to get them open. But otherwise, other than that, I really like tape.
My brother one year sealed all of our Christmas presents with hot glue. So another type of adhesive. All right, well, next, let's watch a video called Dancing Milk, another use for milk.
Hello, I'm Doug Williams from the American Chemical Society. Today I'm going to show you a little bit about fats in milk and how to determine what kind of milk you're drinking. And this is going to involve a little demonstration with food colors and detergent. One of the things that detergents do is they help us mix fat and water, because you know, if you poured oil and water together, they don't actually mix. In fact, they separate. If you shake them really hard, it might get cloudy for a while, but eventually they separate again. And oils are kind of hard to remove with water, aren't they? So that's why you use soap and detergents. But did you know that milk has fat in it and it doesn't separate? You probably wonder how they do that. Well, they pass the milk from the cow after it's been milked into what's called a homogenizer. It's a very small hole with a lot of pressure, and it passes all the liquid through this jet, and it distributes all of the fat globules into very small particles. And once they're in these small particles, then they stay dispersed in the milk, and that helps high-fat milk taste very creamy. If you don't do that, and you let the milk separate, the fat goes to the top and it can be skimmed off. And so you can have low-fat or skimmed milk. Well, we're going to do a little experiment with the detergent today and some low-fat and high-fat milk. And I hope you'll get to see the difference between the two. This is called low-fat or skim milk. And this is more than high-fat, actually. This is called half and half. So this is richer than even the whole milk that you would normally get in a gallon at the grocery store. This milk has extra fat in it. And that's to help you see the difference. Now I'm going to take some ordinary food color, which actually is water soluble. It doesn't disperse very well in fat. So we're going to put a little drop of each color in both of the milks. And you don't have to be very careful about this. You can do this at home with all of these things yourself. You can put those colors anywhere you want. I'm just going to try and keep a similar pattern so that the conditions are the same in both of the bowls. This is red. So now I have red, green, blue, and yellow in each of the milks. And the next thing I'm going to do, so you can see at the same time, is I'm going to dip a little Q-tip or cotton tip swab into my dish detergent here. This is just ordinary dishwashing, hand washing detergent. And I'm going to put it into my milk. Watch what happens. Notice the one on my left, your right side, and the one on the right. They're both showing some color distribution, which we call the dancing milk experiment. The one on the right's kind of slowed down though, and it has big broad streams of color that are dispersing in the water. On the left side, however, there's a little more activity and it keeps on going. And you see it picking up now, faster, faster. What a difference. On the right side, we see colors that are moving slowly and kind of spreading out, and it's pretty. But over on the left, we actually have kind of dance going on. And this is the result of the detergent distributing the fat particles, because there are so many of them. The interface or the surface between the fat and the liquid and the water at very microscopic levels has a lot of energy associated with it. And when the detergent breaks that down, the energy is released in the form of these waves and patterns that you see. So if you didn't know what kind of milk you were drinking, you could try this experiment with a little food color and a couple of swabs and some dish detergent, and you could tell if your mom was giving you the good stuff or the low-fat stuff. Can you tell? I like high-fat milk, but some people don't, and some people would want to avoid that. Either way, you can choose, but you'll know the difference now. Thank you very much.
Well, Amy and John and Paige, I don't know about you, but I know there was a time when we used to have a gallon of everything in our fridge to be able to please everybody. So, Paige, can you give us a little bit more information on the different types of fats and milks?
Sure. So I was thinking about it, and John, do you think it has to do with maybe polar, non-polar?
I think it does, yeah.
Kind of like in cleaning our clothes with detergent? What do you think?
I think so. It's definitely, the water in milk is a polar compound, but the fat globules are non-polar. So they really don't want to be together, but when we homogenize the milk, we force them to be that way. But when you add that detergent, it changes how they're going to interact. And when you add food coloring, you can actually see the movement. So the movement of the particles is going to happen with or without the food coloring, but once you add it, you can actually see it a lot easier.
Ah, so that's why we have like dissolves like?
Yes.
So polar solvents help to dissolve polar solutes. And then non-polar solvents help in dissolving the non-polar solutes. Cool.
And soap is a compound that can help non-polar compounds be dissolved in polar compounds. That's how we can get the oils and grease off our hands when we wash them.
Well, wonderful. Great to know. Next, let's see an experiment that uses a polymer that holds water. We've got two different videos. One is going to be called Instant Snow, and one is all about growing creatures, which you will find one in your resource bag. So let's see those videos now.
Hey kids, did you know that you can make snow inside? Well, today we're going to show you how to do just that with water in a diaper. That's right, water in a diaper. So what we have here is a powder called sodium polyacrylate, which is the stuff that is inside each of the diapers. Now, if you were to reach out, or when you reach out and touch this, you can see that it's pretty gritty and it feels almost like sand and sugar. Now, you might be thinking, how in the world do we turn sand or sugar into snow? That is where our water comes in. Sodium polyacrylate, the powder, is what we call a polymer, which is a fancy word for a long chain. These long chains absorb water through a process called osmosis, and they can grow up to hundreds of times their size and weight. Anyway, that's enough talking. Let's get to making that snow. So all we're going to do is take our water here and dump it into the powder. Now this part is important. You need to watch very closely as to what happens. Are you ready? Here we go. 3, 2, 1, go. So what did you see happen? You might have noticed that the powder, or what we had as a powder before, grew into this nice fluffy snow. So we did it. We made the snow. Now, when you reach out and touch it now, it'll be nice and fluffy. And you might even feel that it's a little bit cool to the touch, just like snow that you would see outside. But what happened to all the water? When I reach out, my hand doesn't get wet. And when I squeeze it, the water doesn't come out. So the polymers, the long chains, like to hang on to the water and don't like to let it go. That's why when a baby goes to the bathroom, nothing comes out. Now, if we really wanted to, we could shrink this back down to the powder using just regular kitchen salt. But what's the fun in that? We like snow better. Well, kids, thanks for joining me today, and hopefully you learned something new. I hope to see you next time.
So you've learned everything there is to know about instant snow, but almost, because there's another item in your resource bag. You may have a dinosaur, an alligator, or a frog. And these creatures are made out of the same polymer as the instant snow. And so what you can do with this is you can put it in water, which I have right here. And I have already done this about 2 days ago. And so now here's a dinosaur. It's been soaking in that water for 2 days, and you can compare it against the original dinosaur. And obviously you can see it's changed. So what you can do at home is you can actually measure this change.
So after every day, you can take out a ruler and see how long, how wide it's grown. If you're in school and you have access to a lab balance, you can actually weigh these. You can start by weighing your original alligator and then weigh this every day to see how much water has actually been soaked up by your creature. Enjoy.
Well, we have some fun things in your resource bag for you. One of those things is the snow, and it's going to come in a bag. Amy's going to show you. That's what it looks like, and it has snow written on the outside of the bag. And then I actually put water in my snow, and I've got quite enough here to play with. So have fun with that. You're going to enjoy that. I'm thinking maybe this is what they use in the movies.
I think you're right, Annette.
To make it look like it's snowing?
Yeah, because snow isn't always there when you want it, right?
Exactly.
Like, I really, really, really wanted snow days sometime, and I really wished hard for snow, and it doesn't happen. And so it's just not always there. So I think people on movie sets, I think they have chemists, and I think the chemists know how to make this stuff. And I think they make snow like this that doesn't melt. And you know what?
That would be fun.
I found out that there's a movie that many of us see in like the winter time. It's called It's a Wonderful Life. It's from a long time ago. It's a black and white. They filmed that in the summer in California with all like this chemical sign of snow. It looks like it's winter, but it's not. It's amazing what chemistry can do.
It is.
I personally like the application on the diapers. And that would be a fun thing also at home if you could get different types of diapers or think about varying the amount of water. You might want to put food coloring in it so you can kind of see it better. There's so many different things you can use your creativity to see what that absorbency is. Absolutely.
Lots of fun. Also in your bag are growing creatures. And you will notice that some of our staff pictures, Megan loves to fish, and Anna was actually holding a crocodile. So if you keep your growing creatures in water for a couple weeks, they will grow up to 3 times the size that they start out at. So we just showed you what 2 days looks like.
That's a lot.
So that's going to be a lot of fun.
Very
wow.
Cool.
It'll be your own life-size friend.
There you go.
I wonder what it's going to feel like, because right now it's kind of hard.
Yeah.
And then after you have it in water, like, do you think it's going to be squishy, or do you think it's going to be hard? I don't know. What do you think, Paige?
I think my hypothesis would be as it grows, it'll start to feel more like a gummy bear.
Oh.
And then if you keep it in the water and it grows even more, it's going to be squishy and soft as it absorbs more water. That's my hypothesis. What about you, John?
I have a similar hypothesis.
Yeah.
I think it's going to be very spongy.
All right.
Probably won't taste like a gummy bear, though, huh?
Oh, no. No.
No.
Not recommended for eating.
No. Cool.
All right. Well, it's up to you young chemists to figure out what the answer is to that. Check it out and see. Are they soft or not? All right. Our next experiment is Oobleck. And that sounds like a name out of a Dr. Seuss book, and it is. Dr. Seuss wrote about Oobleck and about a king who didn't like just the normal, boring temperature and weather of snow and rain. And he wanted something fun and exciting to fall from the sky. And after several Oobleck showers, he decided maybe normal was better. So next we're going to see a video from Sean and Connie, who had a lot of fun playing with Oobleck.
Hi, my name is Mr. Sean, and this is my lovely wife, Miss Connie. We've been doing Chemistry Day for quite a while as volunteers for the museum. And today we're going to be making Oobleck. Now, Oobleck is a very fun thing. It is both a solid and a liquid. you need cornstarch and water. Our water has food coloring in it so that it has color when we finish making it. And basically, we just start pouring in the cornstarch, and then Miss Connie is going to add water slowly. And we just keep mixing it around. If it's too dry, you're going to have to add more water. Go ahead, more water, Miss Connie. It's kind of like making concrete. You got to get the right consistency. You go too much on water, and you have to start over. You get too little, and it becomes clumpy like this. Okay, let's see what we've got here. As you can see, it runs right through my fingers. Yet, at the same time, if you get enough of it, you can make a ball, even though it's a liquid. And there we have a ball. And you'll notice that the ball is starting to melt in my hand. And it can be cut. It doesn't stay a ball for very long because you can see it's becoming goo.
That is so cool.
Now for a special treat, we're going to let Miss Connie throw some of this at me, because you'll see the importance of a lab coat that way. See, if you have a lab coat on, you don't have to worry about getting your clothes all dirty. As well as why you see you should be wearing safety goggles or safety glasses. Goggles are preferred for chemistry.
I won't get you. I promise.
You make it into a ball. And look at that.
See, you just put it there, and there it goes.
And so there we have a nice fun project that you can do at home with just cornstarch and water. What do you think, kids? Sound like fun?
Well, Connie sure had a lot of fun with that. And of course, when you make a mess, it's always responsible to clean it up yourself. So we had a lot of cleaning to do after that. So there's a lot that happens with Oobleck, and you saw that it's both a liquid and a solid, which is a rare thing. And I asked Paige to tell us a little bit more about that.
Sure. So Oobleck is a type of substance we call a non-Newtonian fluid. So as you looked at it and were watching, what was our friend doing when would take some of the Oobleck and push it together and then putting it on the table or on his shoulder? Then there wasn't any force on it or pressure being placed on the actual substance. So do you think it has something to do with the force and the pressure placed on the substance?
I think so, and that's
that non-Newtonian fluid? What do you think, John?
I think so. I know that most solids and liquids, pressure doesn't matter.
Mm-hmm.
They're a solid or a liquid at a wide range of pressures, but maybe it's not the same for Oobleck.
Yeah, I think that as pressure is applied on this non-Newtonian fluid, then it acts or has properties of a solid, where you're pushing those molecules closer together. And so that property of a solid is that you're nice, neatly aligned. And then as the pressure is released and you put it on a surface or on maybe John's shoulder, then the pressure, you're not applying the pressure. And so those molecules can spread out, and it gets properties more like a liquid, where your molecules or atoms, depending upon what your substance is, has a little bit more breathing and moving room. And it only takes the form of the container that it's within. So
yeah,
that's your non-Newtonian fluid, and they're a ton of fun to play with.
Oh, they are. That sounds like something that the Gooey Bandit or Sticky Bandit would love.
Absolutely. Mm-hmm.
Yeah. Amy, is that something you'd like to play with at home?
Oh, I love messy fun. You always got to clean up after yourself, but the best kind of fun is messy fun. So you can do it outside. You can put down like an old sheet or a shower curtain or something, and then get in it, get your hands in it, feel it, gooey. Oh yeah, that's fun stuff. I love doing that kind of stuff. And I didn't know it had a fancy name, non-Newtonium.
Newtonian. After Sir Isaac Newton.
Oh, cool.
Good to know. All right. Our next demonstration and experiment is something not messy at all. It's called magic sand or magic clay.
Hi, I'm Renee Bull. I work at Pfizer Pharmaceuticals in Portage, Michigan. Have you ever been to the beach or the playground and noticed how sand just sucks the water right in? Well, that's because sand is hydrophilic. That means it loves water. But I have this green sand here. It's called magic sand. And the package says that it doesn't get wet at all. That's because it has a nanoscopic, that means really small, coating on it that repels water. It's hydrophobic. It means water fearing. I've been to the beach before. This doesn't seem right. Let's do an experiment to see if this is really true. First, we're going to need to gather some supplies. I have some sand from the playground. I have my magic sand. I have 2 jars with some water in it and lids, a scoop and a spoon. So let's get started. This is just regular water from the tap, and I'm going to take some of this sand and pour it in here. Ooh, it gets kind of cloudy, but a lot of the sand goes right to the bottom. Let's try the magic sand. Well, it goes to the bottom too, but it's not cloudy and it's kind of clumped up. Maybe I need to add some more. Well, that's different. Maybe I need to mix it up some. Let's add the lids. Put the lid on tight before you shake it. Ooh, that's still cloudy. And you can see on the bottom that sand is gathering all together. It looks pretty wet to me. Let's try that magic sand. Shake, shake, shake. I'll shake it extra. It went to the bottom now, but it's still clumpy and it has a silver sheen on it. It looks like there's air bubbles in there. That's a lot different. Let's take some out and put it on paper towel. This is where my spoon comes in. The playground sand is kind of hard to get out of there. Looks wet to me, just like when I go to the beach. Let's put some magic sand out on the paper towel. That was really easy to scoop out. But wait a minute. It doesn't seem wet at all. It's like it was never in the water. Weird. It must be hydrophobic. That's science magic. Now, I mentioned earlier that you can make this at home. So you can make your own magic sand using Scotchgard and playground sand and an aluminum pan. But you're going to need help from an adult. You're going to want to go outside where there's lots of ventilation. Pour your sand into the pan in a thin layer. Spread it out good. Then take your Scotch Guard or Camp Dry and put a thin layer right on the sand. Don't do it too thick or it'll take a long time to dry. Let it sit outside and dry for a while. Then you're going to shake the pan to stir it up and spray it again. You do that a few times with your parents or an adult's help. And then after about 3 or 4 times and it's good and dry, you're ready to experiment at home. You might be wondering, why are nano coatings important? Where do we use them out in the world? Well, we use them at Pfizer to produce extended release medicines. Those coatings help that medicine get out little by little instead of all at once. It's also used for car wax and oil spill cleanup. Pretty cool and important technology. Well, now you know how to make magic sand at home. Have fun, fellow scientists.
Well, that looks like a lot of fun. In your resource bag, you will find a bag of magic sand or magic clay. Ah, there you go. And I've got magic clay, and I put it in water, and it looks like it's floating, and it doesn't mix with the water. When I pull it out, it is still dry. So have fun with your magic sand. I know Amy and Paige and John, you're going to be playing with it soon.
Can't believe they took it out of the water and it was still dry.
Yep.
That's wild.
Nice. Mm-hmm.
All right. Well, next we have a video from Hershel talking about indicators, acids and bases, and how you can write a secret message. Let's watch that one now.
Welcome to the Kalamazoo Valley Museum Chemistry Day at the museum. My name is Hershel Jude, and I'm a member of the Kalamazoo section of the American Chemical Society. And I'm here today to demonstrate indicators. And an indicator is anything that visually shows you something. For example, a smile might show that someone's happy, or a frown will show that they're sad. Those are indicators that we see in everyday life. As a chemist, we use indicators frequently, and one of the main indicators we use is for pH. pH is a measurement of how acidic or basic something is, and pH is on a scale from 0 to 14. And right in the middle is water, or on this piece of paper is blood. It's neutral. If the pH is below 7 and lower, it is acidic. And if it is above 7, it is basic. A very fun indicator is this yellow paper, which you can buy on Amazon. It's called goldenrod paper. And the dye on this paper is pH sensitive. When, if you write something on this paper and it turns red, then the pH is higher than 7 and your liquid is basic. And if the pH is below 7, then you will not see a change on this paper and the material is acidic. Today I brought several different household things. There's baking soda, so it's just a solution of baking soda and water. This is laundry detergent and water, lime or lemon juice, and vinegar. If we write this on paper, let's start with the baking soda. And you can see, when you write on paper with baking soda, you can see that it slowly starts changing from this yellow color to red. And as that sits, it'll get a little darker. And so because it turns red, that means that baking soda and water is a base. When we look at lemon juice in water, and you write the same thing high on the paper, it's right below the red, you will see that there is no change in the color. Lemon juice is an acid. If you write over the red with the lemon juice, the red color will go away and the paper will, as it dries, will turn back to yellow, and you can hide what you wrote previously. And then a couple of other things here we can test. Laundry detergent tends to be basic. It will turn the paper red. And you can see that it is not as bright as, or as dark of a red as the baking soda was. That's an indication that it is not as basic as the baking soda solution. Another common household item is vinegar. When you write on the paper with the vinegar, it is yellow. It does not change color. So one fun thing that you can do with the goldenrod paper is you can write a secret message. So take either the clear wax crayons like you would write on an Easter egg, or in this case, I have just a yellow crayon, and you can write something on the paper, and then you can pass it to your friend. And if they use a baking soda solution and write over that paper, then they can see what secret message you have. Wherever you wrote on the paper with the crayon or the wax paper, it covers the paper and the baking soda does not react with it. So whatever you wrote will stay yellow, and all the surrounding areas exposed to the baking soda will turn red. So as you can see here, I wrote hi. This is a message that my daughter wrote for me this morning. So let's see what she said. Maybe hard to see, but it says, I heart dad. So there are several other indicators that we use in our daily lives as well. Here's one I brought. It's a pool. It's for checking pool water, and this will tell you the pH of the pool water. And in this case, it turns from orange to red for a pH between 6.2 and 8.4. And for pool water, you want it to be just slightly above 7. If the pool water is out of range, it will cause your eyes to burn. So, it's very important to have that right. These are similar type strips that we use in a chemistry lab. And this over here is good for low pHs, acidic stuff. And this one is good for determining the pH of higher than 7, so basic items. And that's a basic, the way that indicators work. You can see that as these papers have set around, the red color has gotten darker and it's easier to see your secret message. And you can also make, there's several items around the house that you can use as an indicator with the help of an adult. For example, a grape juice or cherry juice, when exposed to vinegar or baking soda, will change color depending on whether the compound is sensitive to acids or bases. Another one is red or purple cabbage. If you blend that in a blender with water, you will make a colored liquid that will change colors depending on whether it's you introduce an acid or a base to that. So have some fun, explore around the house. Just be sure to do that with the help of an adult. Again, thank you very much, and enjoy the rest of the Kalamazoo Valley Museum Chemistry Day.
Well, that was a lot of fun. Paige and Amy and John, did you guys ever write messages, secret messages with chemistry?
I did.
I definitely did.
Mm-hmm.
I was trying not to get caught up passing notes at school, but
Yeah.
I think it would have been appropriate, since you're both chemists, that John, if you would have written Paige a love letter with something like that, like that's the way chemists do that, right?
There.
It's never too late.
Exactly. Anniversary is coming up.
There you go.
December, right?
Right. So one of the, I know in the video they indicated some other types of household things that you can use as indicators, and the cabbage was mentioned, and that's one of my favorites to do actually at home, is to take purple cabbage, and he mentioned about in the blender and stuff, but you can also take some water and boil it down with the the purple cabbage in it, and then the extract that you have from boiling that down is your indicator. And it's been really awesome to go and collect a bunch of different other household things that you're wondering about, whether it's like your soda pop or household cleaners or even the lemon juice, and then put that into or put the indicator, the purple cabbage indicator into that, and you'll see the colors change. And then you can look up, what is that pH? And you myself might be able to create your own pH scale, color scale. It would be a fun activity.
It's very fun. I've done that with students before.
Mm-hmm.
Yeah. I used to make rainbows with the cabbage water for birthday parties here at the museum.
Cool.
I'd mix them all up and then I'd put them in order of the rainbow.
I love it.
Well, they're in your bags. You will find two different ways to make messages. One with lemon juice and one with the baking soda. Now, when I was a kid, because one of my chores was ironing, I used to make messages with lemon juice and then used my iron to show what the message said. So I need to actually have your help at the end when the newscaster reviews this experiment. If you hear her say lemon juice instead of baking soda, would you please pretend with me that she actually said baking soda? I think I had lemon juice on my mind when I wrote the script. So I can use your help with that. Our next experiment is about something very, very, very cold. And it's a lot of fun to play with. And we've got a chemist here who's been doing this for years, and he always has maybe a little bit too much fun. Let's watch Brian with liquid nitrogen.
My name is Brian Eckliff. I'm a member of the Kalamazoo American Chemical Society group, and I brought something fun to show you guys today. I have air, but in an odd form. I have liquid air. What I have here is liquid nitrogen. So nitrogen is 80% of the air that we breathe. And normally, I don't think anybody here breathes liquid. You normally need gills for that. And this is what liquid nitrogen looks like here. Liquid nitrogen is liquid because it is incredibly cold. Minus 340 degrees Fahrenheit, 77 Kelvin. It's very cold. It has a couple of very interesting properties that way. So we keep it, because it's so cold, in these little styrofoam containers because they're very convenient. You can get them at the store. Liquid nitrogen is a little harder to get your hands on. But because it's so cold, it has some very interesting properties. The first of which is one that I think most people are familiar with. Is that things that get colder change shape. You know, if you take a balloon like this one, a very nice National Chemistry Week balloon, and we cool it down, we would expect to change. And because the balloon is full of air on the inside, as it gets colder, it reaches something that looks more like that liquid state. I can show you this real quickly because you saw how big my cooler is here. It's about the size of a balloon, and I've got a couple balloons here. It's a lot of fun. We could do this all day. We could just keep putting balloons in here, keep making them disappear. But because what you can hear the crackle, I think, because what is in the balloon is mostly nitrogen. When we get it exposed to the liquid, it gets cold. And what happens to the air in the balloon is it shrinks. And so when it warms back up again, it will re-expand. So you can see our poor little balloons shrunk. And then when you take them out and let them warm up, they usually regain their shape. Every once in a while, one of them pops because it doesn't, the rubber that makes up the balloon gets hard when it's colder. And so they sometimes they pop. But we can do that again, shrink them, warm them back up. Great. It's fun. So the reason why that happens is when things cool down, the motion of the atoms slows down. They don't move as fast, they don't move as far. And the balloon is the size and shape that it is because the gas on the inside is pushing out on the balloon the same as the air in the atmosphere is pushing back down on it. But when we cool this down, the air on the inside slows down, cools down. It can't push as hard against the inside of the balloon, and so it shrinks. When we warm it back up, the molecules move, the atoms move faster, the molecules move faster, and it returns to the state it was in before. So we're going to cool a couple other things down to talk about some properties. It takes a minute, so I'm going to go ahead and get that started. I have a racquetball. It's just a standard racquetball. And I have a banana. We'll give those a few minutes. So you can see the gas escaping the side of my cooler here. Maybe this is a better way to see it. What you actually see here is not the nitrogen. It's actually water vapor. So the water vapor in the air, as the cold gas comes out the side of the cooler, it cools the air that's in this room, and the water vapor condenses out. So what we have here is this little cloud. That's kind of fun because you can usually see it roll right over the edge of the table, and we can get a little cloud waterfall going here. And of course, it's headed down towards the ground because the nitrogen is cold, and so it's a little denser than the air in the room, and so it falls towards the floor. If this were full of helium, liquid helium is fun because it's even colder than the nitrogen, but the helium would head up towards the ceiling because it's less dense than the air. But the nitrogen is more dense. All right, we need to add a little bit more here and keep this cold. We can show you another example of how things get colder as they, how molecules move differently when they're cold. And so I'm going to bring on a volunteer here to help me with some flowers. This is Julia. Julia, which one of these is your favorite? You like flowers, right? That one? All right. Could you do me a favor? Make a little room here. Could you just tap that on the counter? Did you notice anything interesting? No? Okay. Would you mind dunking that flower into our vat of liquid nitrogen there? Ooh.
It's pretty cool.
It is? You want gloves? Let's put gloves on. Do you want to wear my awesome oversized gloves? So these gloves are used to protect hands against the super cold liquid nitrogen. That's why they're so big and fluffy. They're like super winter gloves, right? Huge.
Oversized.
Oversized is right. All right. So could you do me a favor? Pick that up and tap that on the counter again. Tap it. Little tapper. There you go. So do you notice something different about your flower this time?
It's dead, basically.
It's brittle.
Yeah.
Yeah. And that's
again, thank you, Julia. May I borrow my glove back? So what happens is the flour, even though we don't normally think about it this way, the flour is mostly water. And so water is a liquid at room temperature. You can see it warms up pretty quickly. But when we cool that down, that water in the flour freezes, makes ice. It becomes brittle. It's no longer a liquid, it's a solid. And that makes the flour brittle. You can hear the difference. So I have another helper here with me. This is Adam. Adam likes to help with construction at home. And so we have a very special task we need to complete today.
Okay.
We have this nail.
Okay.
We have this block of wood.
Okay.
We need to pound this nail into this piece of wood.
Do you have any hammer?
I have a banana.
That's not a hammer.
It's a banana. It's what we have. We're going to make do. So could you try that again, please? You're getting banana on my nail. This is not working.
No, it's not. It's a banana.
Okay. All right, let's try something else.
Killed it.
Yeah, it's had a rough day. Okay, could you put those gloves on for me, please?
Yeah.
Okay. I have a banana that we've had in here in liquid nitrogen for a few minutes. It's still a banana, but it's a very cold banana. There we go. There's my banana.
That banana does not look very structurally stable.
Are you ready? I need some help here.
Which part of it?
I don't care which part. I think that's good. It works, right?
Rescue banana.
Thank you. Can I have my gloves back?
I guess.
When we froze the banana in liquid nitrogen, it's very cold. It's no longer mostly liquid water as a normal banana is. It's mostly solid water. And that really, you can hear the difference, right? Because it's frozen, because it's so hard, we can actually use this as a hammer now. And we were successful in putting the nail into the 2x4, where we were not so terribly successful with our other banana. All right, I have one more for you. Julia, could you put the gloves on, please? Adam, can you come help me one more time? So I've given Adam a racquetball. I'm sure you're all familiar with the racquetball. They bounce well. They're designed to. It's rubber, it's soft, you can squeeze them, it's pliable, and it bounces nicely. I have another racquetball that has been in the liquid nitrogen here since we started. I'm going to hand this one to Julia. And guys, what I want you to do is stand with the ball out. Yep, Adam, other hand, please, so that they're facing each other. And drop. That is the first time one has broken in a very long time. That's awesome, Julia. I didn't know you had the strength. So what happened? The molecules in the racquetball that Adam has are warm. It's elastic and it can bounce. The other racquetball didn't bounce because it couldn't flex anymore. It had gotten so cold that the molecules wouldn't move and it shattered rather than bounce. So those are the experiments we have for you today. Liquid nitrogen, very cold, minus 340 degrees Fahrenheit. And shows you some of the interesting properties and interesting things that happen to household materials when they get that cold.
Wow. I'm glad he had those heavy duty mittens or gloves. I know I'm not quite ready yet for winter and for having to wear gloves. Amy, are you a glove person or a mitten person?
Depends on what I'm doing. If I want my hands to be warm, I use mittens, right? Because then my fingers get to stay all together. Plus, mittens are usually fluffier.
There you go.
And that's always nice to have something soft and fluffy on your hands to keep them warm. I was going to say that video was really cool. Get it? It was.
There you go. We are full of puns today.
I knew John would appreciate that one.
Yeah. I know he was very careful not to ever get the liquid nitrogen on him, and he used tongs, and he made sure that he was using gloves and sharing a pair. But you know, there's a reason why we wear gloves and mittens in the winter, to keep our hands warm.
Absolutely.
There's some common misconceptions about what freezes and what doesn't within our hands. So I don't know. What do you think, John?
Well, I use liquid nitrogen at my job a lot, and if you get it on your hands, it hurts a lot, especially when they start to warm back up. But even when you don't, and you're just near the cold, like when you go outside and your hands get super cold, and then when you come in, they can hurt. What's actually happening is your body wants to preserve warmth. So muscles around your blood vessels actually constrict to prevent the flow of blood into your hands. And that's why your hands can start to feel really cold, even sometimes on a warm day. And that's just your body trying to stay warm. And then of course, when those muscles stop constricting and all that blood flows into your hand, it can actually hurt a little bit. So that's why if your hands get really cold, sometimes they say you want to put them under not necessarily warm water, but even just room temperature or slightly cold water, and it'll help warm them up slowly to avoid some of that pain.
Exactly, because it slowly brings the blood back instead of a huge rush, which hurts tremendously.
In extreme circumstances, like when you spill liquid nitrogen on your hand, you can
Because
actually
you're not using
wearing
proper
gloves.
safety protocol.
Yeah, you can actually freeze the tissue in your hand, and that's extremely painful too. And if you freeze too much of it, you can get severe frostbite, and you might have to actually go to the doctor for that, because the tissue can die, because as the tissue freezes, little ice crystals form inside your cells and it can damage them. So you definitely always want to make sure you wear gloves when you work with liquid nitrogen. And when it gets cold here in Michigan, you want to make sure you have gloves when you go outside too.
And what I would say to Amy is forming ice crystals within your cells would not be cool.
You punned you back.
Doesn't sound like it. Doesn't sound like it at all. I agree. Sounds like mittens and gloves is the way to go.
Yeah.
Absolutely.
Yes.
Nice fluffy mittens and gloves.
Yeah. Nice fluffy ones. All right, we have 2 more experiments left, and they both have to do with carbon dioxide. Lydia Hines is going to share a very sweet demo, and Doug Williams is going to actually help us determine if we're alive or not. So let's see what those are.
Hi, everybody. My name is Lydia Hines. I'm a chemist in the community. I work as an outreach coordinator, for fun at least, for the American Chemical Society Kalamazoo section, and have done that for many, many years. A lot more than you've probably been alive, you little ones. Anyway, I love to do hands-on chemistry for children. And today is a little different because you won't be here to help me, but you can do this at home too. I like to do experiments that you can do at home. And first I want to tell you what I'm going to do, then I'll tell you why I have gloves and safety goggles and a lab coat on and everything. Okay, first I'm going to be testing for the acidity, how sour candies are. I love sour candies and my friends know that. And so somebody said, I brought you some sour candies for a present. I said, are they as sour as I like them? He said, I'm sure they are. So they gave them to me. I said, I'll test them. And it's real easy to do. So acid means sour, usually not means sour, but acid items are sour, like a lemon, an orange, and usually bases are slippery. We don't eat bases for the most part. We use them to clean with. Bases, a basic thing that we do eat and we have in the kitchen is baking soda. You all have baking soda in the kitchen, I'm sure. So today, the way I'm going to test these candies that my friend gave me is to put them in a plate like I have right here. I have 1, 2, 3, 4. You can see that. Different candies in each one. And I have a solution of baking soda, a solution of this powder in water. It's in a 4-cup measuring cup. And all you do is put about 2 tablespoons of baking soda in about 2.5 cups of water, and you dissolve. That makes a solution. When there is most of the baking soda is gone completely, you have a solution. You want to take that off here and put it in a cup. And I'm going to be doing this experiment in a minute. First of all, I also want to tell you that I'm going to wear gloves. I'm going to say, doing chemistry in the kitchen, you need to wear gloves. Well, you know, even though we're having fun, when we do chemistry as chemists, right now, this activity is to help you learn how to be chemists. We wear gloves to protect our hands from spilling. We don't know, baking soda won't hurt us, candy won't hurt us, but we never know what we're dealing with. So if it spills, we don't want us to get it on our skin. Neither do we want to get it in our eyes. I'm going to wear my safety goggles. Don't want to get any spilling in our eyes because that might hurt. We want to have a lab coat on. I won't, well, I can button one button. I can find the hole. There we go. And my feet are covered. We want to make sure that any spillage doesn't get on our skin or on our shoes or anything. So now we'll do our experiment. I have candy in this one, you can see. This one, number 2, number 3, number 4. I won't tell you what they are. I was just testing them because he brought them and said, you'll like them, they're sour. So I said, okay, I'll test them to make sure you know what you're talking about. So I'm going to pour baking soda solution in the first one. Baking soda and acid will usually give us a gas. I told you I'm using sodium bicarbonate, which is baking soda. Maybe I didn't say the name, but that's what it is. And do you recognize the word carbon in there? And all of you hear carbon dioxide lately. Sodium carbonate with acid will give you carbon dioxide. If it reacts, nothing. Okay, let's try this one. It's bubbling. Just a little. Okay, that's acid, all right. It may be sour, really sour, I don't know. This one, that's bubbling too. Okay, my friend was right. There's sour. Now let's try these. Wow, look at this bubbling. My goodness. Well, anyway, as far as I'm concerned, the most sour is this one because it gives me the most bubbles. This is the most sour. This is sour. This is sour too, but this one sure isn't. So he learned something. I know that I like these now. I'll tell you what they are. These are round candies. I don't know why he thought they were sour. These are called sourdoughs. These are sweet tarts. And these are warheads. I know what I'm going to go to the store to look for is warheads because I love sour candies. So there's just a little spoon. So, wow. Do you see the bubbles? You see the bubbles here? These are all sour, but these are the most sour. So anyway, that's our experiment. We have these candies that aren't sour, and there was nothing to bubble. There are these that are sour, yes. These are sour too, but these sure are sour according to the experiment. So I told you what they are. The warheads take the prize. They're the most sour, and so I'm gonna like those. And hopefully my friend found out that I do like sour candy. Well, I hope you like this experiment. Have fun doing it at home. And remember, if you have baking soda and acid, you will get carbon dioxide, which will show you how sour something is. It's very sour, it'll really bubble. It's kind of sour, it'll make some bubbles. It isn't sour, it won't do anything.
To have a life, you have to be alive. And today I'm going to talk to you a little bit about how you can prove it. That's an interesting proposition. You probably thought you were alive. You probably are if you're watching this. But hey, somebody might make you prove it. So we're also going to talk a little bit about carbon dioxide. Many of you have heard of that. It's a gas in our atmosphere. It's not a very abundant gas, but it's present, far below 1% in air, but it is important to us, and it has a lot of consequences. One of the things that I'm going to talk about today is how we get carbon dioxide, and it's largely from what we call combustion, or the combination of carbon-containing fuels with oxygen. It's oxidation or combustion, and the products of that are water and carbon dioxide. Now, there's a lot of water in the air as well, and a lot of carbon dioxide, but there's a lot more oxygen. Air is about 20% oxygen. That's the air that you breathe in. But when you breathe it out, it's only 16% oxygen because your body uses it. Well, what are we doing with that oxygen? Well, think about it. Fuels like coal, petroleum, wood can all be combined with oxygen. And when you do that, you get energy back, like fire and heat. And we can use that to drive turbines and make electricity. We can use it to power our vehicles. And so we use carbon fuels and the reaction with oxygen quite often in our lives. But we also use it in a personal way. Wood is really made up of fibers that are a bunch of small sugar molecules. And you can't eat wood, and it doesn't taste very sweet because your body isn't set up for that, but you can eat sugar. And when you do that and you breathe in oxygen, the combination of sugar and oxygen can result in a combustion process that produces carbon dioxide. When you breathe in 20% oxygen, breathe out 16, and you breathe out carbon dioxide, which is the product of that reaction with sugar and oxygen. And when you do that, you create energy for your body. Thankfully, you don't catch on fire. But I'm going to prove this to you now that I'm breathing carbon dioxide. So I'm going to need some lime water. Lime. Now, where does that come from? Well, this is called lime water, and it doesn't look like a lime, but its name comes from the chemical that's in here called calcium oxide. Lime is called lime because when you heat up limestone, calcium carbonate, you can make calcium oxide. And then when you put calcium oxide in water, it becomes calcium hydroxide. So blame the geologist for the name. It's called lime water. So this has calcium hydroxide in it. And I'm going to pour some into 2 cups so you can see what's going to happen. One with me breathing into it, and the other one just sitting there. When lime water captures carbon dioxide from my breath, it's going to reform limestone. Now, I already told you that calcium hydroxide is soluble in water, so it's nice and clear. But when it forms limestone, do you think it's going to be soluble? No. Limestone is not soluble. That's why it's a mineral. So watch this. I think you can see the difference. I'm alive. This is calcium carbonate forming in the solution here. And I could do the same thing in this one, of course, because it started out the same way. But I think you see the point. I have carbon dioxide in my breath, and when I breathe it out, it forms the salt, which is insoluble, and proves that I'm alive. Now, that was pretty obvious, right? But you never know. I don't know what kind of things you're into, but if you thought I was a robot, a zombie, maybe you'd want me to try this just to be sure. What else could you use it for? Well, you probably already knew about this, but carbon dioxide dissolves in water as well by itself when you don't have lime in it, and it just dissolves in water and forms an acid called carbonic acid. It also creates a lot of fizz in things like soda pop and seltzer water. So you can enjoy that as the fizz on your tongue. Also, carbon dioxide can be used to put out fires because it's a product of combustion. It doesn't support combustion. So I'm going to show you an experiment you can do at home. I can't do it here because I'm not going to be allowed to light a candle today. But if you have a candle in a jar, you can do this experiment. This is baking soda. You probably have some in your kitchen. And I'm just going to put all this in the bottom, which is what you would do. A couple of tablespoons is plenty, I think. And then I put a candle in here. And I would light that candle in the jar. And you know what happens when you add vinegar to baking soda? You might have seen this before, but acid and baking soda will make carbon dioxide. And as soon as you do that, you have to pretend that this candle is lit. And by the way, you can try this. Light your candle and then pour in some baking soda or some vinegar on the baking soda. And you'll see the fizz at the bottom. And when the carbon dioxide comes up, it'll envelop or wrap itself around the flame, and you'll see what happens. Carbon dioxide is used all the time commercially in fire extinguishers. See those fire extinguishers hanging on the wall? Well, you can lift those up and pull the trigger, and some of them will shoot out a nice stream of carbon dioxide, which is a gas, right? And so it puts out the fire and it doesn't leave any residue. So it's one of the more popular kinds of fire extinguishers for fires of electrical equipment, which you wouldn't want to have get water on them or some other chemical that puts out the fire. So carbon dioxide is very important for that as well. Finally, oh yes, I wanted to ask you about baking soda. You wondered, what about baking soda? Well, it's got carbon dioxide in it that gets released when the acid is poured on it. It also can release when you heat it. And if you made cookies before, you probably used some baking soda. Otherwise, those cookies were pretty crispy. The baking soda during baking will release carbon dioxide and puff up the cookie so that it tastes nice, soft, and moist. So carbon dioxide is useful for what we call leavening or adding air to our baked goods like cakes and cookies. One last thing about carbon dioxide. You know, too much of anything can be bad. And even though carbon dioxide is very helpful, we can overdo it. We're always making carbon dioxide when I breathe, when I bake cookies, but also when I burn fuels. In fact, we do that a lot. Fuels like coal and petroleum, natural gas are used to heat our homes, to power our cars, and generally to make energy. So when we do that, we increase the amount of carbon dioxide in our atmosphere. The more carbon dioxide, the warmer the planet gets. Now, this is having some long-term consequences to our climate and our weather and to all the things that grow and live on this planet. So just a reminder to be conservative in your habits, to not use more than you need, to save energy, and to save some for someone else. Thank you.
Well, that was very interesting. One of the things that you are going to find in your bag is a special balloon, a Mylar balloon from the American Chemical Society, and it inflates all by itself. So Paige, will you share with us how that happens?
Sure. So there's the little vial in there, and
I don't know if you can see it.
Mm-hmm.
Yep.
So Annette, what's in that vial?
It is citric acid.
Okay.
So,
and inside the balloon, you would have probably a powder in there.
Mm-hmm.
And Annette, did it say what the powder was?
It's baking soda. We just talked about that.
We did it, didn't we? So we're gonna, when that vial breaks with the acid and then it mixes with that baking soda, it's going to produce carbon dioxide, just like what we saw in the video. Well, that carbon dioxide is a gas. And that, does it seem to be sealed all the way around? Is it?
It is very sealed.
All right, so that gas, CO2 that's produced, is going to collect within that container or the balloon. And so as more gas is produced, you're going to see it, what we would say, inflate. And there's your balloon.
There you go. We're going to let you do this because it says you need to step on it. I was hoping I could do it by hand. And no, you really need to step on it. So we're going to get to our very last video. It is our last newscast with Sara Slippery. And she's going to review all of the experiments we just saw. And she's going to compare them to the exhibits that you again will find at the bottom of the website that shows some of the exhibits in the museum and where the Sticky Bandit may have done his crime. So let's get to that last video now.
This is Sara Slippery reporting to you live from the WKVM Newsroom. We have been following the story of the Sticky Bandit who broke into the Kalamazoo Valley Museum, rearranging the artifacts and exhibits, and then framed one of the staff members. We are thankful for the local chemists who have provided explanations of the many gooey clues left behind by the bandit. Let's review those clues one more time so that we can solve this crime quickly. Julie Bauer showed us how to make glue from milk. Do you think the bandit was hinting at the many dairy-related products found in the farmhouse kitchen exhibit? She also showed us how strong that glue was when she glued two pieces of wood together. That really widens the field because there are so many artifacts made from wood that were disrupted. Could it be the guitar exhibit, or the mummy sarcophagus, or perhaps the tools found in the bog iron exhibit that intrigued the bandit? Doug Williams entertained us with the dancing milk experiment. This could be the farmhouse kitchen exhibit again. There's a butter churn on display. Or the milk jugs found in the suburban garage. Maybe the bandit was referring to the planetarium, where one of the new programs displays a low-volume fireworks show, similar to the way the colors dispersed when the dish soap separated from the water from the fat in the milk. I never realized how much fun chemists can have. Matt Barringer started talking about diapers, but ended up playing with snow. There is a sleigh, a sled, and a toboggan in the Kalamazoo Direct-to-You exhibit. Do you think the Sticky Bandit likes winter? It was fun watching the substance that absorbs water work so quickly and seeing how dry it was when it fell from his hands. Carl Stachew used that same chemical reaction that Matt talked about to show us how growing creatures work. There are lots of things that grow in the museum. The tornado grows from vapors into a funnel when wind comes from all four directions and there's an updraft in the air. The tornado is one of many weather-related science exhibits in the Seasons of Southwest Michigan Gallery. The rain garden out front is filled with native plants that have been growing in this area for centuries. Pfizer donated growing frogs, fish, alligators, and dinosaurs for the resource bags. If the bandit likes to fish, perhaps he chose the Shakespeare fishing reel exhibits? Or perhaps he remembers the lizard mummy that was once on display but is now in the collection storage. Do you think the bandit came to the museum when he was a child? Sean and Connie Bashaw sure had fun playing with Oobleck. No wonder Dr. Seuss wrote a book about it. The idea that Oobleck can be both a liquid and a solid was so interesting. Can you think of an exhibit in the museum that represents something that can change from a liquid to a solid? Water can be a vapor, a liquid, and a solid in the form of snow and ice, so the bandit could have been looking at the tornado exhibit or the sleds. Milk is used to make butter, so it could have been the farmhouse or the garage. Renee Bull experimented with magic sand and magic clay. She talked about them both being hydrophobic, meaning it is fearful of water or repels water. In Michigan, we are surrounded by the Great Lakes and lots of sand. She showed how to make magic sand from the sand we can find at the beach, using a water-repellent spray like Scotch Guard. There are several science exhibits in the Seasons of Southwest Michigan exhibit that talk about the properties of sand in Michigan. I never knew the same process was used to coat pills so they release over time. The bandit may have grown up in the Kalamazoo area and taken a tour of the Upjohn facility years ago, or grew up on their vitamins. There are 2 exhibits on Upjohn in the History Gallery, one at the entrance of the Kalamazoo Direct-to-You Gallery and the medical section of the History Gallery. Hershel shared about indicators, what I like to think of as kitchen chemistry. How many of you grew up writing secret messages with lemon juice? Now we know how it works. I wonder if the bandit used some of the supplies in the farm kitchen to write the message. Or maybe he was inspired by the stained glass window across from the mummy exhibit. A well-kept museum secret is the hidden message written in Morse code in the window frame. Let's just keep that between us. Brian Eklov and his children had a lot of fun experimenting with liquid nitrogen and dry ice. These are so much colder than snow that I'm sure the bandit wasn't referring to the sled exhibit. Just maybe he saw one of the planetarium shows called Ice World that tours the planets looking for ice in our solar system. Remember all the safety tips they shared with you if you ever have a chance to study liquid nitrogen. Who would have guessed that Lydia Hines, a founder of Chemistry Day at the museum, likes sour candy? Do you think just chemists experiment with candy to see which one is sour? Many years ago, Egyptians figured out how to preserve bodies by mummification. They used a salt known as natron to pack the inside and outside of the body to dry it up like a pickle. The sweet substance of honey has also been used to mummify bodies. Finally, Doug Williams returned to share an experiment on carbon dioxide, that bubbly substance we all love in pop or soda. I loved his explanations about all the ways we use carbon dioxide, from figuring out if we are breathing to adding fizzle to our pop, to showing how it can put out fires. Throughout the museum, we have special fire extinguishers he referred to that won't harm the artifacts like water ones will, and instead uses carbon dioxide. Now it's up to you. You have met the staff, observed all the local chemistry experiments that relate to the clues left behind by the Sticky Bandit, and we have related those clues to the exhibits. Use the riddles provided to help you decide who, which staff member was framed, where, which exhibit or artifact the bandit picked, and the how, which chemistry experiment helped identify the crime the most. We want you to let us know what you think happened. Be creative, use your imagination and problem-solving skills to help us solve this Chemistry Day mystery. This is Sara Slippery, signing off.
We are at the end of our program. Please make sure to check our museum website and you will find this sheet. We'll walk you through. You can pick one of the 10 exhibits, one of the 10 experiments, and one of the 10 staff, and create your own solution to this mystery. Remember to send it in to me by 5 o'clock on Thursday, and on Friday we will be posting all the answers and have a poll, and you will get to pick who actually, what the actual solution to this mystery is. I want to thank all of my co-hosts and the interpreters, Lizzie behind the scenes running all the videos and helping us do this program, and all of you, our visitors, who will help solve this crime. So up until next time, remember that this is your museum, and this is the Kalamazoo Museum signing out for now. Welcome and thank you.